Okay, so
Ready
our
to go?
first speaker is Brian Sales from Oak Ridge National Lab, and he's been here, I think, twice before.
No, just once before.
For the first one.
The first one.
Yeah.
The first one.
So the first, and hopefully this isn't the last.
Yeah, well, depends on my schedule.
Thanks, Brian.
Well, I first want to thank JP, Nick, and Efren for inviting me back to talk a little bit about sort of the basics of how to prepare high-quality research samples, particularly single crystals of quantum materials. And so this is an outline of what I'm going to be talking about. First, I'd like to just go over briefly our group, who we are, the types of synthesis that we do, the type of research that we do, and what we work on. And then I'm going to go over some fairly simple but surprisingly important guidelines for making any material, including things like taking care of paying attention to your starting chemicals, weighing everything, writing everything down, getting familiar with phase diagrams, thinking about crucible materials, different crystal growth techniques, and then since we work a lot with neutron scatterers, scaling up the crystal growth to grow larger crystals. And I'm going to talk about a new crystal growth method, which is sort of a variation of a flux growth technique, but it's called liquid transport growth, and it's some similarities to vapor transport that was developed by Jianqin Yan in my group. And then I'm going to talk a little bit about the importance of characterizing what you grew rather than rushing to do the physics before you know what it is you're measuring. And the goal of all of this is to avoid the curse of humorothery, which is written there at the bottom. And unfortunately, this is still somewhat true today. And I'll just read it. This is a paraphrase. Humorothery was British, and he would be quite a bit more obtuse about what he's saying. But he says, physicists often make beautiful measurements on crappy samples, while metallurgists make crappy measurements on beautiful samples. So that's what we're trying to avoid with this first talk. So this is actually part of the correlated quantum materials group at Oak Ridge. It's gotten bigger over the last few years, and it's a nice mix of sort of senior people, mid-career people, and early career people, as well as quite a few postdocs. And David's going to be talking a little later in the week. He's a professor at UT now, but he's still part of the group. And Michael McGuire and Andrew May and Chao Jinyan are some of the main staff members, but we also have others as well. Athena has a project, and Andy Christensen, who's primarily a neutron scatterer, but we also do some material synthesis, so he's also part of the group. So what we work on, basically it's discovering characterization of new quantum materials, hopefully with some relevance to an energy technology or an information technology. Sometimes, though, it ends up just being cool physics, which is all right. In the past, we've worked on thermoelectrics, superconductors of various types, permanent magnets that don't involve rare earths, unusual magnetic ground states such as heliumagnets, skyrmions, etc. And we're still doing some of that. And the more recent research is focused on sort of more hardcore quantum materials as defined by the modern definition, things like quantum spin liquids, cleavable magnets, or 2D materials that have honeycomb or Kagami layers. This is, everybody likes to look at pretty pictures of crystals, and let me see, get my, there we go. And you can read what they were looked at for. But the thing I wanted to point out was this material was grown by floating zone. This was grown by vapor transport. This was grown by vapor transport, and also this liquid transport growth, which I'll talk about a little later. This is essentially a Bridgman or a gradient freeze technique. This was liquid transport growth, floating zone. both types of flux growth and liquid transport growth. This is flux, floating zone, and vapor transport. So we grow crystals by a wide variety of different techniques. And of course the hard part is finding out what material you want to grow. That I can't, in a short lecture, tell you, okay, this is going to be an interesting material. A lot of it's just experience, a lot of it's taking insight from theory, and some of it's luck. This is, once you sort of know what you want to grow, there's a whole bunch of different crystal growth methods. I realize you can't probably read that, but I've highlighted, this is from Pamplin's crystal growth book, which is a good reference. And I've highlighted with these colors the different types of crystal growth techniques that we use routinely in our group. And so we do quite a few. And the difference is basically you're growing it out of a solution, either water or a metal molten flux, or you're growing it directly from the melt, or you're growing it from the vapor phase. So deciding what technique to use is important, and you have to sort of learn something about phase diagrams, learn about the characteristics of the material you're trying to grow, and then decide on the appropriate growth method. These two require the least amount of effort and sometimes can produce really good research grade samples. The floating zone technique, as Stephen will talk about, is a little more labor intensive because you have to prepare these polycrystalline rods. And there's a lot of places where you can fail along the way. But this is relatively low labor intensive. So this is some of the equipment that we have at Oak Ridge. We have 3 floating zone furnaces. We have an old NEC furnace, which is really good for oxides, such as this manganite single crystal that was grown in the furnace. There's another one, which is a 4-mirror crystal systems furnace, which also has these ferrofluid magnetic seals. And what that does is it allows you to get a pretty good vacuum in the system, so you can actually grow intermetallics as well as oxides as well. And this will go up to about, I think about 9 bars of overpressure of gas. We also have what's called a high pressure floating zone furnace from Schiedra in Dresden. And this basically is, it's a pretty fancy system and allows you to apply 150 bars of gas pressure, which is basically the pressure in one of these compressed gas cylinders. So it's a pretty high pressure in that sense. And you can, if, for example, for growing this particular this is a ferromagnet, but it's also a quantum paraelectric, barium iron 12 oxygen 19. You had to apply over 50 bars of oxygen pressure to get this phase to grow. So in some situations, this is a sort of unique capability, but it's sometimes difficult to find a material where it really justifies all the work to use this thing. And I'm sure Steve's going to talk a lot about that. So just the sort of the basics of the floating zone technique, since I have this really nice picture from Yen. You have 2 polycrystalline rods that you've made in a conventional furnace typically, and you're counter-rotating them, and you're applying via these mirrors. You have a high-powered lamp that focuses the radiation, the infrared radiation, on a very small region, and you basically melt the region between the 2 polycrystalline rods, and the surface tension is what's holding everything together. So there's no crucible, so it's clean if the rods are clean. And then you move this zone up and down, and hopefully you'll leave behind a single crystal. We also have, and you'll see some of this I think later in the afternoon, arc melting is a great way to sort of first prepare a metallic sample. It's sort of instant gratification for synthesis because you can do something in about half an hour. You essentially put the elements that you want to melt together on a water-cooled copper hearth, apply in an argon atmosphere and argon plasma, which is generated by a welding power supply, basically. And then you can melt any materials. You can melt tungsten in this. And this is a good way to, for example, mix, say, nickel, cobalt, and chrome to make a material. You can also do drop casting in this to make rods. Sometimes, if you're lucky, you can make rods that will go into the floating zone furnace. We also have sort of a unique circa 1965. We have a lot of old equipment sitting around at Oak Ridge. This is a home-built arc melter which runs with a pretty large welding power supply, and you can handle about 100 to 200 grams of material, which if you're doing something like Trikowsky growth and want to grow a big crystal, this is very handy. You can also seal tantalum aluminum tubes in this thing, and it's connected to a glove box that you can pump out, and so you can also handle and arc melt things that are reactive in air without exposing them to air. This is an older picture of all the conventional resistively heated furnaces in our group. It's quite a bit more crowded now. We have a lot more people working in there, so we probably have twice this number at this point. We also have some Bridgman gradient freeze capability systems, and we can also do traditional solution growth. This is the sort of thing that you buy. You can buy these kits from like Edmund Scientific, where you can like grow crystals out of a water solution. Sort of the same idea, except we often use deuterated water for neutron scattering. And these particular furnaces, which I can't remember the name, it's a Japanese company, really have very good temperature control, like within a tenth of a degree. So you can grow really nice big crystals out of aqueous solution. Here's one that actually Wei Tian grew in this furnace. Metal flux growth. This is one of the more common techniques and the most versatile technique for growing crystals of new materials, particularly intermetallics. And normally, if you don't know much about the system, you'll use 2cc alumina crucibles. There's a little alumina straining piece. This is basically a piece of alumina with some tiny holes that you're going to centrifuge the flux through, the molten metal. You can buy, these are called Canfield crucible sets because Paul convinced this LSP Industrial Ceramics to produce these in both 2cc and 5cc sizes. So in the case of something like manganese bismuth, which I'll talk about in a minute, you put in this case, about 0.3 grams of manganese, 30 grams of bismuth. Well, that won't fit in this, but scale that down for 2cc. A little bit of manganese, a lot of bismuth into one of these alumina crucibles, put the frit on top, stack the other empty crucible on top, and this goes into a silica tube. You put a little quartz wool at the top and the bottom, and then you seal it. This is our sealing station at Oak Ridge. And you then can seal these alumina crucibles in either an argon atmosphere or a vacuum or partial pressure, whatever. And this is actually Byram Saparoff, who is a former postdoc, sealing one of these ampules in using the hydrogen-oxygen torch. And Byram is now an assistant professor, or maybe associate professor by now, at the University of Oklahoma. He did very well. And so this is one way to seal these tubes. Everybody has a slightly different method. This is called the fourfold way of sealing the silica tube. This is the easiest for people who aren't very good like me with doing this, and so I offered to show them how to do this last time, but if you want, I can do it again. Anyway, and then you seal this up, and then you put it in a furnace, have some temperature profile. When you get to the right temperature, which I'll discuss in a moment, you pull this out of the furnace when it's hot, throw the ampule into a centrifuge, and then centrifuge off the molten excess flux. And if you're lucky, you'll end up, for example, with nice crystals of manganese bismuth, or here's an example of a cadmium silicon diphosphide crystals, which are pretty red in color. So I'm going to go into some of the more mundane stuff now, which is surprisingly important. In terms of safety, all of the elements or the compounds that you order from the vendor will have with them a material safety data sheet. Unfortunately, we found that these sheets have to include everything, and so everything is dangerous at some level. I mean, you can drown in water, you can suffocate in helium gas, but in most applications, water is not that dangerous. So what we decided was that this is a much better guide. I think I picked up one of these books in the 80s. We were working on these thallium-based superconductors, and I wanted to know exactly how toxic thallium was because I hadn't worked with this. And this is a really good guide because it allows you to compare sort of the true hazards and sort of the relative toxicity to something that you're familiar with. Like you could compare thallium to lead, for example. And so in terms of making compounds where you're making them for the first time, this is a really good guide to decide, you know, how you're going to have to handle this material. For example, some things for like barium or arsenic, barium particularly you have to handle in a glove box because it's sensitive to air and it's flammable, particularly in fine powder form. And then arsenic, of course, can cause cancer. Arsenic you can work with briefly in air, but if you leave it out for very long, it turns black. It forms an oxide. So it's important you can look at the materials safety data sheets, but I'd really recommend something like this. And then read the labels very carefully. As I mentioned, some of these chemicals you have to handle in a glove box. These M. Brown glove boxes are probably the best I've seen over 30, 40 years of doing this sort of research. Working in glove boxes is not fun. I don't know anybody who really likes to do this, but these are probably the best in terms of giving you a lot of visibility and a lot of ease of handling things as easily as you can for working in a glove box. I mean, your hands get all sweaty, and you have to have gloves on so you don't stick to the rubber here. But these M. Brown things are pretty good, and they also have a nice readout so you can quickly assess whether your atmosphere is good. It should be less than about 0.1 ppm of water or oxygen. So, you buy your chemical from the vendor. You say, okay, great. It's 99.99% pure. Well, the first thing is, I think this has happened about 3 or 4 times, but this is over like 30, 40 years of research. The vendor puts the wrong label on the bottle. And in some cases, that can really be dangerous. For example, they sent something labeled zinc or tin. It was actually zinc. Now, if you heat tin up to 1,000 degrees C, you haven't got a problem. You heat zinc up to 1,000 degrees C in a closed environment, you got a problem. It'll explode. So, if possible, if you think there's something wrong, it doesn't look quite right, it's good if you can do a quick EDX analysis or a quick X-ray pattern just to check to make sure that you've got the right element or compound. The other thing that is pretty sneaky from the vendor, this is particularly for like rare earths and other metals. They'll say it's 99.999% pure, but they don't mention, they only check for other metals. They don't check for oxygen or chlorine or other carbon particularly. And there's a really interesting example, Ruthenium Trichloride. There's been a lot of work done at Oak Ridge because this is a quantum spin liquid, and this is what was on the bottle. Actually, it was only about 25% of this phase. The rest was ruthenium metal and these two oxychlorides. And needless to say, when you tried to vapor transport this, you didn't get the right phase. This is another example. Again, there's a lot of old chemicals that probably at University of Maryland too, sitting around that's been here for a while. We tried to make some neodymium copper oxide. This is 20, 30 years ago. And about 30% of the weight of the oxide was actually water. So rather than being a bright blue, it was a pale blue colored powder. And this is something I learned the hard way. Apparently the organic chemists know this. When you buy something from an organic compound, it has some of that in it, but it's usually got a lot of other junk, and you have to filter out all the junk. And so if you work with sort of a hybrid organic, inorganic compound, it'd be good to go talk to an organic chemist who might have some ideas on how to purify it. Yeah.
Metal spaces.
Yeah.
I also learned recently that not only is that true, but they often exclude the highest contaminant in their percentage.
Yeah.
So if there's some other metal that's 1%, they just ignore them.
Yeah, I mean it's hard to get hafnium without any zirconium, for example. But usually they'll tell you that. That's like 4%, but
especially the non.
Yeah. No, it's you have to be skeptical from the vendor. I mean, they're trying to sell you something. Okay, this is, David always laughs when I put this up here, but it's really a very powerful technique. I'm really a fan of guys like Lavoisier and Langmuir, who could do these really clever experiments with almost no equipment and come to these profound conclusions. And Lavoisier, who in many ways was sort of the father of modern chemistry, the reason he was able to provide all this tremendous insight about different chemical reactions was that he could weigh stuff very accurately. And this is a picture of Lavoisier's, not a very good picture, of Lavoisier's balances in a Paris museum. But because of this, he could tell, for example, that when iron oxidized, it didn't lose weight, it actually gained weight. And so that sort of, that very basic information. So particularly if you're doing a new synthesis recipe and you want to figure out whether it's working, if you weigh at all the steps, you can actually tell what's going on. You can tell if your carbonate actually really did give off all the CO2. You can tell if some of your ingredients need to be dried more. You can tell if something reacted with a crucible or something evaporated out of your reactants. And so it's a fairly simple but useful technique when you're trying to make particularly a new compound. Okay, this is something which should be obvious, but it's surprising, particularly with crystal growth, how many things you could write down. The furnace you use, the growth parameters, that's pretty obvious. The local weather sometimes is important if you're growing things like in an air in a platinum crucible. The humidity can affect things, how the powder is mixed. I mean, it's really as much information as you can write down that you think might be relevant. It's extremely important. And this is something, I don't know how many people have had this experience. I've had it a lot. You grow some pretty good crystals the first time. You try to reproduce the recipe and you try to tinker it a little bit, make them better, and they always get worse. And then typically it takes about 6 months to get back where you were before. I don't know if anybody else had this experience, because you're going to make them bigger. And I'm going to give you an example from our own research about the flux growth of alpha manganese bismuth crystals. This is a really good ferromagnet. And it's very interesting material because the anisotropy actually gets stronger as you get closer to the Curie temperature. That is, if ferromagnet, you have the spin pointing along this one direction, the energy required to flip it into the plane, that's the anisotropy field or anisotropy energy. And for manganese bismuth, it actually gets stronger, and that energy gets larger as you get close to Curie temperature, which is really a desirable property for a ferromagnet or a permanent magnet. And so we wanted to grow crystals and study why that was. Well, it was very strange because, I mean, nobody had grown these before. Which I thought was sort of odd in the literature. So I went to the phase diagram. So this is the other book that you're going to want. This is Okamoto's phase diagram of binary alloys, and these are basically all pairs of elements in the periodic table. Now 153, have on page 153 the bismuth manganese phase diagram. So here's temperature, here's the atomic percent of manganese. Bismuth is 100% of, let's see, which way are we going here? Yeah, I think this is, yeah. So this is the bismuth rich end. And so the phase we want is right here, and the liquidus is this line, this region up here. And so if you choose a composition here and you cool down this liquid, the first phase solid that precipitates out is manganese bismuth. Now it is a long ways over, and this region is only, it's pretty low. It's only about 80 degrees, 90 degrees C, and it's at low temperatures. But still, I mean, you should be able to get crystals. And so I tried this, and this is sort of the weights. I use 10 cc crucibles, which I get the glass shop to help me with this, because I don't have a lot of time. So if I want to grow something, I grow a lot of it. Anyway, so this is the recipe, the temperature profile. And sure enough, we got these beautiful crystals. And one of the crystals weighed about 2 grams. And this one was actually used from a beautiful spin wave analysis. We sort of understood the magnetism in detail from this analysis. And we also did some polarized neutron measurements where we were able to see the small moment on the bismuth. But so we did this, and then about 6 months later, we wanted some more crystals. We said, well, we'll just go grow some more. And the subsequent growths, I only got these really sub-millimeter sized crystals. There was really nothing usable, and I couldn't figure out what. I checked the starting ingredients. I tried to go back to the original source of the manganese, the bismuth. Nothing worked. I changed the profile a little bit, and it didn't work. And then I finally went back to the old notebook and looked, and I noticed that in the original growths, at about 1,000 degrees C, which is way up here, I actually reached in with tongs into the furnace and then just shook the ampule to kind of stir the manganese and the bismuth a bit. Turns out that was the key. Then I got big crystals again. But if I hadn't written that down, my memory would have not probably remembered that. So that's one example of why it's really important to write stuff down. Crucible selection. There's a whole variety of things that you can use for either flux growth or for preparing polycrystalline samples. We typically use aluminum oxide, silica, so we have some platinum crucibles for growing oxides, and tantalum. And really, even when you're doing the floating zone technique, you still need some type of crucible, for example, to put your polycrystalline rods in to center them. So it's important to think about what reacts with what. And this is, I think this may be in the book or the handouts. This is a table taken from Intermetallic Compounds by J.S. Westbrook. This is actually his chapter on formation techniques from 1967. And what it tells you is for different classes of materials, you probably can't read this, but like for alkali metals, alkaline earth, It'll tell you what the suggested crucibles are, and it'll tell you what sort of cover gas that it works the best. And so this sort of old information back when industry was doing a lot of research into growing crystals and making materials is extremely valuable. It'll at least give you some clue as to what sort of crucible to use. And it goes on here to rare earths. So this is another good reference if you can get a hold of it. Now we have a really good glass shop at Oak Ridge. And we often will have them make customized ampoules like this silica ampule, which is appropriate for Bridgman growth with a little point here, or you can have a little extended pointed region down here. You can sometimes get away with things that react a little bit with silica. You can reduce that reaction by putting a thin layer of acetone on the inside and then pyrolyzing it, basically carbonize the tube. You have to be careful when you do this because there can't be much liquid left because acetone will flash. But you can do this with a hydrogen oxygen torch pretty easily. And then for the larger ampules, I tend to like these 10 cc crucibles like here. This has to be fabricated in the glass shop. That's really sort of beyond what most people can do with just an isolated torch. You have to have special lathes that allow you to work with this silica tubes that are that large. So,
can I ask a question?
Yeah.
For these larger ones, are they able to do that with the tube and the back, or is that?
This is open, yeah. Yeah, so they can't do if you have something really reactive. Yeah. So scaling up. And Jeff will appreciate this. I mean, we actually think about, since we're at Oak Ridge with two neutron sources, how one could make the crystals a little bit bigger so you can do, for example, inelastic neutron scattering. And one thing is, if you have a glassblower, make friends with them because some of these scaling up techniques require these specialized ampules. And so the 10 cc size, which is shown here, this is about the largest that will fit into a standard centrifuge that you can buy. We've tried to actually get somewhat larger centrifuges, but this seems to be about the biggest you can get without getting a ridiculous machine. You can get around that to some extent. I wouldn't suggest this with the current safety environment, but this is a manual centrifuge. And so this is a bucket, a 5-gallon bucket. And you have a stainless steel can here, some fire bricks, a fire brick on the bottom, and some quartz wool. And you could take something up to about 250 cc out of the furnace, dump it in the bucket. Now, when I used to pitch softball, this was easier. But then you have to warm up. And you have to do this. So and the faster you spin it, the more effective the liquid removal is. And Julie will appreciate this. I actually grew some pretty large 14111 crystals using the manual centrifuge. But, okay.
Brian?
Yeah.
Not worried about that.
What did I say?
You're not worried about the excess tin and antimony?
No. It's mainly tin that comes off. It's a 10. That's going to have a 10 flux. No, yeah, it's molten, but it'll work. You just have to be a little careful.
Sure your handle's on there.
Yeah, well, yeah, you have to do a few practice runs. Safety runs, yes. May have to edit that out. I'll probably get calls from our safety people. Okay, I'd like to briefly discuss this transport growth method that Jiacheng Yen came up with. And the reference that describes it in more detail, in case I butcher the description too badly, is given here, where there's lots of examples. And this again came because we wanted to grow larger and more crystals. And the basic idea is something like this. So this is the standard setup you have for vapor transport. You have your starting materials here at typically the cold end, or the hot end rather. It can be reversed depending on whether the reaction is exothermic or endothermic, but I'll just say this is the hot end for now. And you have some transport agent, and you have a temperature gradient, and you end up precipitating crystals out of the gas phase at the cold end. You can do something similar. Your starting materials are here, but in this region, rather than having gas, you have liquid. And then you can precipitate the crystals out of the liquid phase. So it's sort of like horizontal flux growth. So the question is, why would you do it this way versus sort of the normal way? Well, this is one example. This is the only science pretty much I'm showing in here. So we had this interesting material, molybdenum-3 antimony 7. There was a question of whether magnetism was involved in the superconductivity. And we've got this phenomenological guideline, which we cooked up, looking at a lot of different superconductors, was that when you measure the thermal conductivity just below Tc, not down well below Tc, just below Tc, the thermal conductivity always goes up for unconventional superconductors, and it did for this one. And there's also some other indications. This is a phase diagram versus pressure. They have superconductor and spin siglants. There's a dimerization or cubic to tetragonal phase transition that occurs actually at 0 pressure at about 40-50 Kelvin. Anyway, so the idea was to make enough of these crystals so we could look for the neutron resonance. And if you sort of do a back of the envelope calculate, if you say this was yen with the 2cc crucibles, you'd need over 20 gross to get enough material. And so he was trying to come up with a way not to do 20 gross. And if you look at the phase diagram, it's kind of interesting. There's very limited solubility for molybdenum in antimony, but there's only one phase, which you don't even see. It's right there. There's this molybdenum-3 antimony 7 phase is the only phase in the diagram. And so what he did was, maybe you can see this. He put molybdenum at one end, pre-melted the antimony here, and this was the temperature profile, and this was over like a week. He was able to get, these are the crystals sort of entrapped in the antimony flux. He was able to cut out a lot of pieces pretty easily of the molybdenum-3 antimony 7, and he generated a lot of material pretty quickly. So this was one of the examples of why you might want to do something like this. Another one is iron 3 tin 2, which has a double Kagami layer compound, some interesting topological properties. But if you look at the phase diagram, there's a very narrow temperature region between this line and that line where this phase formed, which we want over here. And so if you try to do this from the liquid phase, which is over here, it's a long ways away and you haven't got much of a window. So again, what he did was put the iron at one end and then filled up the rest of the tube with tin, and basically isothermally heated this thing in this interval. And he got all of these crystals of iron 3 tin 2. Yeah.
By the way, I shouldn't be the only person asking.
Yeah, feel free to stop me. I don't bite.
So my question is, do you know how important it is to keep the, in this case, the iron at one end when you start? I mean, rather than just mix it?
Yeah, well, I mean, there's a lot of questions about this technique, but essentially it's more like the vapor transport where the iron diffuses in through the liquid phase, you hit a solubility limit, and then it precipitates out. And it continues to go. I mean, yeah, I mean, there are some questions about this technique in general. But I thought I'd bring this up because it is fairly new, and I haven't seen it presented anywhere, so I thought I'd talk a little bit about it. And so you can also, this was the previous two examples, the liquid was part of the material you're trying to grow. In the case of all these other materials, like osmium trichloride, iron selenide, actually you can grow ruthenium trichloride the same way. What was used was an aluminum chloride, potassium chloride flux. That was the liquid. And it works for all these different examples. So it's an interesting technique. This is sort of the comparison between the horizontal and the traditional vertical flux growth. We don't have to mix the charge in the flux, or you don't want to. There's no homogenization at high temperature. There is a temperature gradient, small temperature gradient across the horizontal axis. Anyway, you can read that. But there's really needs to be a little more work to see, how useful this is. I think that basically it's an interesting technique if you need a large amount of crystals in one growth, or if the window is really narrow. Yeah.
How difficult is it to extract the single crystals in the salt?
Yeah. In this case. Well, I think in the case of the other, using this flux, I think this washes away, as I recall. So the water will dissolve that flux. But in the case of this one, you'd have to basically cleave them out with a razor blade. It seems to work pretty well for the aluminum-3 antimony 7. You can get some pretty big pieces. But that's, worrying about the flux, that's actually my next point. Go ahead.
How is it that, so that you take the entire tube and put that in the oven horizontally, or you only put one side?
No, the whole thing goes in. Well, you can put it in a tube furnace, and you can have a slight gradient in one example. But I think for the iron 310-2, I think it was just, as I recall, it was isothermal. But in that temperature window.
So it uses as whatever you're trying to get to fall solution, it fuses across the flux.
Yeah, right.
How do you, so does it only work for low concentration?
No, well, I mean, basically, if you're sitting at this temperature, the only phase that's stable is that one. And so that's the only phase that's going to precipitate out of solution. And you tend to get larger crystals near the end, and then smaller crystals as you go back toward the original charge. At least with the molybdenum-3 antimony 7.
Temperature gradient, even if it's an isotope, is it a box for the moment?
Yeah. There's sometimes a gradient. Well, there's always a gradient in most furnaces, but I think in this particular case it was quote isothermal. Yeah.
Liquid transport growth. So do we need to put horizontal or like inclined or something?
No, it's flat.
Right.
It's horizontal. Is that what you're asking?
How this liquid transporting and getting crystal only one corner instead of only down?
Well, I mean, you basically, the starting ingredients diffuse through the liquid and precipitate in the liquid. And so when it's melted, of course, the liquid, I don't know if I haven't got a picture of this. The liquid is, will be, like half the diameter of the tube, more or less.
The schematic diagram you showed, like crystal is forming at the corner of the...
Oh, at the corner? Yeah, it forms all the way, let's see, which one was this?
Yeah.
like that. Yeah, it forms all the way across. This was just to sort of make the analogy with vapor transport. He obviously used the same picture for that. These are Yen slides.
The other key is that you don't raise the temperature up. Like, do you just raise it up to
Yeah. The growth, yeah.
that you want to form?
Yeah, right.
You sit there. So
You sit there.
The iron's mostly not going to melt, right?
No, it doesn't melt. But it will. Yeah, but it will dissolve. It's very slow. Yeah, and I know I had looked this up actually before I came over here because I couldn't remember. For the molybdenum-3 antimony 7, it took a week for all that, which is not bad. I don't know. I think for the iron, I think the iron 310-2 it took longer because it.
Different than a flux core where you usually melt everything.
Yeah.
And slowly cool.
Yeah, no, it's different. It's different. Yeah, it's closer to vapor transport, except you're transporting through the liquid. That's why he calls it liquid transport growth. Okay, where were we?
For 5 minutes.
Okay, all right. So there's only the last thing, the importance of characterizing what you grew. And this is really important if you don't want to succumb to the Hume-Rothery curse. If you do Bridgman growths, it's a good idea. The composition typically is not homogeneous because you're freezing the melt out of a liquid, and the liquidus line is very often not flat. And it's good to, cut, at least sacrifice one crystal, cut it up, look at the composition and the properties at all points in the crystal. And this is for, growing a really large crystal. In flux growth, you can get multiple phases. Sometimes you get some interesting new materials that you weren't expecting. And flux inclusions are always a worry. And I'm going to give you an example in a minute of why you have to worry about where the flux is and the properties. And I've seen a lot of examples in the literature which basically have multiple pages of mathematics and equations explaining the results when it's clear in the one measurement they were doing, they had the resistivity voltage leads across an antimony inclusion and the leads for the Seebeck coefficient across the entire crystal. And so they ended up with some astounding power factor, a really low resistivity, really high Seebeck coefficient, but it was essentially because they had an inhomogeneous sample and they were measuring property A on one part and property B on the rest of the crystal. And this, we all make mistakes in doing this, but particularly for you guys who are starting out, it's extremely important not to make too many of these types of mistakes because it can really ruin your career. I know several people that are really good scientists in general, but they sort of rushed and did this, and now nobody believes the results that they report. And so particularly for the first few things that you publish about exotic measurements on a particular new compound, it's really important to make sure that you know as much about what you're measuring as the measurement. And so I'm going to show you an example. This is this is an interesting material. It's got this iron 2 phosphorus structure. There's 2 iron sites. Here's one of the sites, the magnetism tends to be more itinerant, the other site more localized. This sort of composition is close to compositions that are really good for commercial magnetocaloric refrigeration applications. So it's an interesting material, and this was kind of the first millimeter-sized crystal ever grown. I was very proud of myself. Out of a 10 flux, it's got 4 elements plus the 10, and you get these beautiful, 5 millimeter long crystals. And so I said, great, we'll measure the properties. So here's the resistivity versus temperature, And you see, oh, it's got this huge magnetoresistance at low temperature. That's wonderful. And the resistivity at low temperature is about 2 microohm centimeters, which is very low for this sort of material. And magnetoresistance is about 750%. But that struck me as odd because iron 2 phosphorus itself, the resistivity is several hundred microohm centimeters. So there is something wrong with this data, even though it looks very smooth and convincing, and you see there's a black shiny crystal. If you looked at this crystal more carefully, in cross-section you found out it had a tin core. Magnetoresistance of tin at 4 Kelvin is 50,000%. Something to keep in mind. If you grind away all this material, so you're measuring just this region, you actually end up with the resistivity, which is at low temperatures 440 microhm centimeters. You can see the Niel temperature very clearly, and there's almost no magnetoresistance. So this is probably the most important point of this lecture. Make sure you really know what you're measuring, and don't just immediately assume because it's a shiny black or silver crystal that it's a high quality crystal, which drives me nuts when they say that in the literature and there's no evidence that they did anything to measure any of the properties of the crystal or any of the characteristics of the crystal. So that's actually my last slide.